So documentation for Essentia looks like this. So first thing I'm going to do is I'm going to present you a little bit the algorithm that you can find in Essentia, so you have an idea of what you can find in there. Because basically, I told you that with Essentia, it's used to extract features from audio for song or from sound effects from an audio file. It would be more correct to say that it's a collection of algorithms that you can use to do this. It would be like, if you want, you can think of it as a Matlab toolbox. So there's like all these algorithm functions, and then the part that which says, okay, here's an audio file, and I give you back all the descriptors, is more something that we did as an example, but the idea is that you use Essentia, like in Python for instance, you can use it to do research, which is what we're going to see. We're going to do it, we're going to work as if we were in the Matlab environment. It's written in C++, so you can embed it in anything you want, but there's the Python bindings which we're going to use because it's much easier. You can work, it's interactive, you can do nice plots and everything, and you don't have to compile and blah blah blah. So I'm going very somehow quickly to skim over the list of different algorithms. So the first thing you have to do if you want to work with audio, so you need to have like something that is able to load audio from audio files. So there's different types of audio loader which are all derived from the same, but are kind of useful. So the audio loader just loads the file that you have, but then you have one which is the mono loader, which is going to load it for you and downmix it to a single signal. So if you have a stereo file or mono file, you don't care. You use the mono loader and you just get a single array of values. The good thing with all of those is that they use FFmpeg. So for those of you who don't know, it's a library, libraries library that pretty much can load everything. The one that you have in PLC, MPlayer also has some bindings to that, which means that with Essentia you can load audio from WAV file, which is nice, but you can also load directly from MP3, from OGG files, you can load from Flash videos, you can, everything pretty much that you can throw at FFmpeg, you can throw at Essentia also. And there's the associated writer files. So once you have your audio, you process it, you do whatever you want with it. If you want to write it, you can also write it to a file. Same, everything supported by FFmpeg. So you can write to a WAV file, but you can also write directly to MP3 and everything. There's one other, this one, which is audio access marker, which basically I'm going to show you how it works. But if you have time events, like for instance the beats in a song, and you have the song, you want to put those on top of it, and it's going to write it in a single file, so you can actually hear the two of them superimposed. The one thing that it doesn't have, Essentia, with respect to this, is you cannot play audio on the sound card. And you can write to a file, and then you can open the file in your player or whatever, but you cannot say like Essentia.play audio and listen to it there. Okay. So for standard signal processing, we have frame cutter, which takes an audio stream as input, like a file, and like cuts it into frames for you, because usually you want to analyze in like small sections of time. The windowing, which does like typical windowing that you do before the FFT. The FFT, which is a complex fast-forward transform. You have the spectrum. You have a few more. For example, if you have an audio that's like 44 kilohertz and you want to study it at 16 kilohertz or vice versa, some autocorrelation, there you go. You have some statistics. So by statistics, I mean things like the mean, the energy, central moments, variance. Basically, you take a series of values and you find one single value that describes it. Median, flatness, and some of them very standard. There are also audio filters. So there's you have generate IAR filtering, and and you have some which have already been specialized on low pass, band pass, and high pass. So you just say I want a low pass filter that gets everything above like 2 kilohertz, and it generates automatically the coefficients for you. DC removal that removes the stable component of the signal. Equal loudness and skip it. So all of those were pretty standard, and you also have descriptors which are more tuned to music information retrieval. So you have bark bands, med bands, MFCC coefficients, which are used a lot. Just to know, if you don't know what those are, then it's okay. It's just, if you know what they are, just know that they are in Essentia, otherwise that's fine. HPCP, which is also called chroma features, is like to know whether you have like a more of a C or E major in a given spectrum. You have a few that are used for music classification, like the whitening, so that like, all the peaks are the same height, planning. There are a few descriptors. Those ones are more used for sound effects, because they make more sense on very small sounds, like they do not necessarily make sense on strong. For speech, MPC is used a lot in speech, for instance. There are tonal descriptors, so these are descriptors that are more used when you do tonal analysis. So pitch detection detects what's the pitch of a given frame. There's the key, there's a chords detection that outputs a sequence of chords. So if you have a song, it's going to say like, well, first you have a C, and then you have D major, etc. A few descriptors also that try to describe whether your frame is harmonic or not. That is, if it's like perfect chord, very nice, like C, E, G, then it's very harmonic. And if you have like two semitones, then it's not going to be as much harmonic. Some rhythmic descriptors. So basically, this is BPM analysis. So it tells you whether it's 120, 140, or this. Plus some assorted descriptors that are used for the BPM analysis, but are kind of hard to explain in 30 seconds. Here are some more sound effects descriptors. So like log attack time. And there's also high-level descriptors, which are much more high-level, and usually they're not computed on the audio directly, on the spectrum directly, but they're computed on some mid-level descriptors that have been computed on the low-level descriptors. So basically, you go each time one step higher to try to have that's the reason they're called high-level, because you don't derive them directly for the audio itself, but you kind of build them on some intermediate descriptors. So danceability, for instance, returns whether a song is danceable. So if it gives you one, it's most likely to be like dance or techno music, and if it gives you 0, it's going to be like whatever, free jazz or well, that's the idea at least. Few other we have SPX is segmentation. So for instance, when you have a song, you have like introduction, chorus, bridge, chorus again, whatever. This algorithm will give you the time at which there are separations. So we'll say intro, but it's not going to say intro, but it's going to say there's a part from 0 to 10 seconds, and then from 10 seconds to 1 minute, it's a different part. There's onset, computes the list of the onsets. So onsets is when a node, more or less, it's when a node starts. So it's going to say new node here and here and here. Gaia transform, I'm going to skip over it at the moment. I'm going to talk maybe a little bit more next week when we talk about Gaia. And then there's also complete extractors. In Essentia, you can use different algorithms and put them together into a single one that does everything that the small one did, and so that it's easier to work with. So for instance, if I say I want all the low-level descriptors that you can compute in Essentia. Instead of saying I want this one, this one, this one, this one, this one, and this one, there's one which already does all of those, and it's like low-level instructor, for instance. And there's a few that are used, for instance. All the tonal features are in one extractor, all the rhythm features are in a single extractor. Yeah. So that's just to give an overview. There's a complete reference, so that's the complete list of algorithms with just look at it very quickly. So you have all the algorithm. For each of the algorithm, let's say HPCD. It's nicer if you look at it on the white screen. You have the inputs. So for instance, this one has two inputs, frequencies, which is a vector, and magnitudes, which is a vector. And you have one output, HPCD, which is a vector. You have a few parameters that you can use. And yeah, that's the parameters. And you have a description that says what the algorithm does and some references in the literature. Okay. Yes. So I'm going to start Python. So before Essentia, I'm happy because it works. So now the idea is I'm going to show you how to do a simple feature extractor. So for instance, you may not know what this is, but like MFCCs, so a Mel frequency coefficient, some C coefficient, which are very used. So I'm going to show you how we extract MFCC for a single file. And this part, it'd be nice if you follow with me, like if you do it with me. So I'm going to go slow, I'm going to type everything to type so you get a feeling about it. And you can actually download, you can take any sound that you like, or file that you already have on your computer. In the page here also, you have same file here, which contains like a small, like 8-second wave file or MP3, I don't remember, and a few files that give the easier version. You don't have to use it, it's just that in case you did it or don't have it in the database. Yes. Okay. Okay. One thing I didn't say, in Essentia, so we have all those algorithms, and they exist in two versions, nearly all of them, because Essentia can work in one of two ways. One is, let's say, Matlab way, like the way we're going to do it now, where you just like say compute the FFT of this frame, and then you plot it, and then you have the plot, and it's interactive, but it's more than interactive, it's imperative. It's like a typical way of programming. You say, tell the computer do this, and then do that, and then do that, and it does what it's telling. There's another way, which is called the streaming mode, where it's more like, I don't know if you know PureData or this kind of stuff, where actually you create a graph of algorithms, and you connect them, and then you say, okay, run, let your graph run, and then there's the audio that comes in one side and flows to the graph, gets processed, and then ends up at the other side. In which case you don't actually tell the computer what to do, you just say, you connect like the boxes, and then you let the stuff flow in it. Most of the algorithms exist in both versions, but there are some that do not because they cannot. Right now we're going to look at the standard mode. So standard, kind of weird word, but that's the streaming mode. So all the algorithms are in Essentia.standard. In Python, you can either import a module, or you can take everything that's in the module and import it into your local namespace. So I don't know if you've seen this syntax last week. Basically, this says take everything that's in Essentia standard and import it here, which means that now everything that was in Essentia standard, which contains the list of all the algorithms that I showed you before, are in my, so for instance, I have centroid, I have the FFT. I do it this way because it's easier, so I don't have to type essentia.standard.centroid each and every time. There's also one thing that's nice, so in normal Python, you have to do help. All the algorithms have documentation, which is the one I showed you in the web documentation, but it's also available online. So if you help centroid, you have the same help, for instance, for the centroid algorithm. All of these are you need to care about. And ePython, that's an ePython feature, but it's nicer because you can also put a question mark at the end and set it up, and it gives you the help. It's basically the same. Okay.
When we type then, it's not working. It says name.
When you type?
Then, for example. C-N.
Yeah, okay. Sorry. Okay, that's the tab completion. So when I type send, what I do usually, like works on Unix, Windows also sometimes. You type the tab and you get, okay, so here go to send, and then central moments or central, so I put an O, central, and I type tab again, so I get central.
Okay.
The send here is because I typed send and tab, and then it showed those two. But if you look at it, here, that's the third command, and here I'm still at the third command. Meaning, nothing is actually happened. It's just like asking me for more output. Here, for instance, I was at the first one, for Essentia, it worked, so then next time I go to the second one. There are a few other features from my IPython. I'm not going to go over all of them. I recommend you read the documentation, but there's lots of nice features. You can save sessions or not, or for instance, if I want to edit like the first command, type end first, I can edit it like in my editor, and I say, okay, I didn't want to import Essentia, I wanted to import whatever, and of course that doesn't exist. But okay, just keep in mind. Yes, also, if you see anything that looks weird or sounds weird, you don't understand, just interrupt me. Like, so the same thing, like, just stop me, ask me, and okay. Another thing about this, so you have all those algorithms. Right. They're all objects, so I don't know how much programming you did, but if you use Matlab, for instance, and you want to use the FFT, you just say FFT of my array, and you get the result, and FFT is a function. In Essentia, there are no functions. These are all classes, so you need to create the objects first. You need to instantiate them, like to say, I want an instance of this object. And then you can use as if it was a function. Because this is done because the advantage of objects over functions is objects can have a state. So for instance, FFT doesn't matter because the FFT of an array is always the same. If you want to do filtering, for instance, the filter is going to have a state. Like you filter audio and it has a short-term memory. And when you say filter of something, it depends on the memory of the filter. And depending on the memory of the filter, you don't necessarily have the same results on the output. Like if you have complete silence and then you filter some audio, it's not going to give you the same result as if you have white noise and then you filter the same thing, because the filter is changing. Or let me think of something else that has states. Well, there's one, and then there's also the advantage of objects is that you can configure them. So let's say you want to compute the MFCCs. You say, okay, I want 10 coefficients, or I want 20, or I want 5. So you can say, first of all, I create an MFCC object that's going to compute the MFCC for me, and I want this MFCC object to be configured so that each time I call compute on it, it gives me 5 coefficients using 40 energy classes. So that means that before you can use all of those, you need to create them. So for instance, if I do, I cannot do FFT of 1, 2, 3, 4, 5. It's not going to work. What I have to do is, first of all, I have to create an object. So this is the way that you create an object. So create it. And then you can call the FFT on it. Well, that's not very. FFT is simple, it doesn't have a state, but if you have, let's take the centroid, for instance. I'm looking at the documentation of the centroid, and you see that it can take one parameter, which is the range, because you might want to compute the centroid of an array, and it might have different range. For instance, if you're computing the centroid of a spectrum, the range of the spectrum usually is going to be from 0 to the sample rate, like it's your language frequency. If you have an audio centroid, you want to usually have the index of the audio samples, so the range is going to be the length of the audio. That depends on which type of centroid you want. So if I want to say I have, like, let's say sample rate equals 100. I want to have a spectral centroid. I can do spectral centroid is my centroid, and I configure the range equals okay. That's the way you create an object, and you give it the parameters when you configure it. This is equivalent of saying why? Yes, okay. I put a dot at the end because sample rate here is an int, and I want range to be a float actually, so I divided by 2. In this case, actually shouldn't have changed a lot. No, it doesn't change. It doesn't worry. Because it gives the same value, and then internally it converts it to float anyway because it expects to float. It's just like habits. Yes. This is equivalent to creating your centroid without playing, and then saying configure range. The first way is just faster to type the second one. Most of the values, again, I'm going to look at the documentation, looking at the centroid because it's an easy example, have a different value. If they don't, I mean, given that it has a default value, I can create a centroid and do not specify this parameter, and everything's going to be fine because it has a default value. If it doesn't, you need to specify a value for this parameter. Otherwise, you won't be able to create the object. It's going to tell you, hey, there's no default value. What should I use for this parameter? And that's about it for the basic presentation. So now we go back to our initial goal is we want to compute the MFCCs for a file. So the first thing we want to do is we want to load this audio file. So I'm going to use the monoloader, so very simple, take I get from input. So let's start by looking at the documentation for the monoloader. As you can see, the monoloader doesn't have an input because it's not getting audio from anywhere or whatever. It's just has a single output, which is the audio, because that's what you get at the end. Has a few parameters. For instance, told you this is monoloader, always gives you a mono output. So depending on whether you have a stereo file, you might say, okay, maybe I only want the left channel, or maybe I only want the right channel, or I want to have a mix of both. So that's this. You need to give it the file name, of course. No default value, doesn't know what file to read. And you need to give it the sample rate that you want. The monoloader also does resampling, so that you know you're always working at the same sample rate. Description, yeah, okay. So I'm going to create my monoloader. I need to give it a file name. So here I could type the name of the file directly. I put // times the file completion. You can see IPython is quite smart. It can autocomplete lots of stuff. So for instance, if I type / here, it completes from the files that are in the current directory. So I want to take this one. And for the rest, I'm just going to use the default values. So that's the maybe tricky part. Once you get used to it, it won't be anymore. What has happened here? Absolutely nothing at the moment. Because what did I do? I created the object that is going to load the audio. But it didn't do this thing yet. So if I want to load the audio, I need to call it a call function. So that's a bit tricky for, in this example, you say, okay, that's a bit contrived, it doesn't look very natural. There's a very good reason behind it, which is that everything's an algorithm. There's not, half of the things are algorithms, the other half are functions. And it's also so that you can actually, in the streaming mode, it's very important that you have this distinction of what is a parameter. Like the name of the file is a parameter, it's not an input. There's only one output, which is the audio that you load, and this only happens when you say to the algorithm that is created, okay, start doing your stuff. So for instance here, if I want the audio, I need to call the loader. In this case, there's no input, so this here is empty. Okay, so here you can see the audio is an array. Once you've done this once or twice, you get the hang of it. It's going to make more sense for more complex algorithms because then you're going to see really the difference. But for loading audio, it might look a bit strange, but just accept that there are reasons. So we're going to play very quickly with Matlab. I don't know if you did that last week or not. Because they're not all zeros. It's just because we only see the beginning and the end. I'm going to actually show you that they're not only zeros. So Matlab has different ways of working. You can have very nice. It has Matlab kind of compatibility mode where you have all the same function and they have the same function names as in Matlab. So I'm going to use this one. So it's called PyLab. Same as Essentia for the algorithm, I import everything from PyLab because I don't want to have to type PyLab whatever each time. And so there's a few functions in PyLab. The one I'm going to use is plot. So let's say I want to plot the first second of the audio. So audio now is an array. This is a NumPy array. Okay. which means that you can do lots of stuff with it. Yes?
It has to be mono.
It has to be mono.
Yeah, it's mono.
No, no. No, I just do it mono because it's easier.
But if we don't have them 5 monos, how will we convert it into monos? It's possible with the down link?
I have no idea. I guess.
So we cannot load an stereo file and then put the down links to the left channel?
Yes, if you want to load the stereo file,
Yes.
you just use the audio loader, which loads and gives it to you the way it is. So if the audio loader loads a mono file, it's going to give you a single channel. If it's a stereo file, it's going to give you the 2 channels. Here I use the mono loader because it's easier for me and I don't care.
And if you load a stereo file in a mono loader?
Yes, it mixes the 2 channels together. So, like for instance, okay, so let's forget about the stuff. Let's get an audio loader. So if I load this file, here the audio loader, let me show you the documentation first. It's going to be able to tell one more thing. So as again you see, it doesn't have any inputs, but the audio loader has 3 outputs. So that's like also happens in Matlab, but it can return you like different things. So in particular, it's going to return you the audio signal. It's going to return you the sample rate at which the audio is encoded. Because the audio loader is the most basic one. It doesn't do anything for you. It just loads the stuff as it is and gives it to you. As you saw, mono loader does the mixing and also does the resampling. So here, as it doesn't do anything, it tells you the sample rate, which is a real value, and it tells you the number of channels in the file, which is an integer. And in this case, here you see that we have an array of stereo samples. So basically, it's 2 values, so one for the left, one for the right. And it tells you it's 44 kilohertz, and there's 2 channels. So basically, if you say that's the way also you get back different values in Python. If I call loader 2, gives me the 3 values. Actually, it's one tuple which contains 3 elements. So you could say result equals loader 2, and then you have audio equals result 0. Right? You have sample rate equals result 1, and number of channels equals result 2. Which would be a way of doing it, but there's a faster way which says audio sample rate and number of channels equals result. Because as you see, result is those 3 values. So instead of saying like first values equal result first value, second value equals result second value, you can, this is called unpacking. Because you have tuple is packed and then like you unpack it just by giving the names. Okay. If you try unpacking and it's not the correct number of arguments, it's going to tell you that I have 3 values and you're only giving me 2 variables, so I cannot do this. This is a Python thing. This has nothing to do with Essentia or OMP or anything. Okay. So I get back to the video I had before. There's another, probably if you've used IPython, you realize very quickly, you can go back in the history with the arrows. So this is like up and down arrows. So if you remember you type a very long comment, like 3 comments above, you can just like look for it with the up arrow. If you start typing, for instance, code, and you look with the up arrow, it only looks with the comments that start with this. So So here it only looks with the stuff that starts with audio. Okay. It remembers this between sessions, so if I exit and I start in Python again, I still have my history, everything, so it's nice. And you can also look backwards or forwards in the history. As here we're at the end, we look backwards with Control R. This is the same as bash, for those of you who know. And you say, oh, I remember I typed something with like 554, so you say 554. Ah, yeah, that was a line. You see, it's looking for this, and this is the last line that it found that contains it. This is an IPython feature. Just little notes as well. Okay.
For working,
Yes?
you have to work always with command line or work with
No, you can work with an editor. I'm going to show you the editor just after the one. I'm working here because because it's nice, it's interactive, and I can show you stuff while I talk. Yeah, you can work with an editor, of course. Okay, so I get my audio.
Sorry, a very basic question. How do you actually get into that folder of 554
This one is contained in the Essentia tutorial and zip file that you can download from the Aula Global.
And how do you get into that folder?
CD, okay. In IPython also you have the basic commands like CD and everything that work directly. So you can see dot. Here, you can ls. These files are the files that you find in the Essentia tutorial unplug.zip file.
Okay, thank you.
Okay, another feature of IPython, which can be really nice, is like cd and ls, like this very simple command that you use all the time, they work naturally. But if you want to execute something in the shell, which is not a Python command, like let's say, let's say you actually want to listen to this file. So I want to listen to it with mplayer. You can start the command with a exclamation mark, and then you can type the command that you want. So for instance, if I type this, it's going to execute mplayer, but as if it was in a normal shell, and when it's done, I go back to the Python shell. Right, so it's still there. And here I get back to my Python interpreter.
You have typed the root out to the file. What is that? Play it?
This?
Yeah. The name of the file.
Yes.
Okay. Like show them the folder.
Yeah, the complete path. For instance, if I go here and I want to listen to it, player, I will here, Essentia, this tab, underscore tab again, okay, 5, then let's start with the 5, tab, so just to make sure that the audio loading works, I'm going to plug it. So I plug the audio, let's say the first second. So first second, there's like 44,000 samples. So this is slicing operation, it's the same in Matlab. This means from 0 to 44,100. The 0 is not necessary. And the plot doesn't do anything, it returns an object to me. That's nowhere. To show it, I have to type show. There's a mode for IPython that interacts with Matlab that you don't have to type show, and you can open as many windows as you want, but you need to start IPython with Matlab. Okay, just very quickly. So here I started IPython normally. I do my plot and then I need to show it. And it's here. So as you can see, looks good. Because you plot the whole audio.
No, I got the part, but the part that is in the 44 is in green and the other part is in blue.
If you plot multiple times, it's going to plot on the same plot. So to create a new plot, it's the same as in Matlab. You have to type figure. Okay, so for instance, what happened was this. Then the figure looked like this, because the first time I plot all the audio, and here I plot, but always on the same plot. So you get the two, and it's green because it looked for a different color than blue, because this blue for the previous one. If you want to plot multiple, say plot this one, which is fine, then you can figure. This is exactly the same as Matlab. Okay, create a new empty here, and then you plot this. And now I have two plots, which is this one, which is the complete file, and this one, which is just the first second. Okay. So we have our audio now. It's here. It's a nice array. And we want to compute the MFCC. So the MFCC, you don't compute it on the whole audio because it doesn't make sense, which you do and you usually do like lots of time. You take your audio and you cut it into small frames, which represent a moment in time, and then you do your analysis on this small frame. In particular, let's look at the documentation for the MFCC. It says that it takes as input the spectrum. So we don't compute the MFCCs directly on the audio, but we're going to have to compute the spectrum first. And then it outputs, like here, for output stuff. So what are we going to do? What are we going to need? Sorry. So we're going to need the MFCC. We're going to need the spectrum. There's one thing, there's the FFT algorithm in Essentia, which gives you the complex FFT. So we could take the complex FFT and then compute the magnitude of the FFT, which is what we want. There's a spectrum algorithm that does this directly and is a little bit more optimized. So we're going to use this one. It's also simpler. Before computing this, I don't know if you've done some other stuff, but before computing the FFT of a frame, you need to window it, because otherwise you get lots of border effects, which are very nasty. So we're going to need a window. So there's the algorithm which is called windowing. Takes input and output, and has type of window which you can choose. You can do zero padding and zero phase, which we're not going to talk about here. And okay, so let's start by creating those. So let's say we want our window, and we say we want window. We want the spectrum. So what I'm doing here is I'm instantiating all the algorithm first, and I'm configuring and everything, so that after that I can use them directly. So spectrum doesn't need a lot of configuration. We need our CC algorithm, which I'm just going to take the value by default, try changing the bands and everything. Okay. And okay, so I have my audio, I have my algorithm, and usually what you would do here is you would do a for loop. No, actually it's kind of hard to read. You would Matlab, you would segment it yourself, and you would say start index, end index, and then you would jump all of this by hand. In Essentia, as this is a very common operation, we have there is a frame cutter algorithm which cuts the frame for you automatically, so you don't have to do this by hand. You don't have to set the jump index yourself. You just say I want frames of size that much, and I want you to hop that much. But that's an algorithm like all the others. We have to give input, output. And in Python, we have something which is much easier, which is a frame generator. This one probably doesn't have any interesting documentation. The frame generator, do you know what a generator is in Python? Basically, a generator is something, kind of a list, where you say which contains a sequence of values, and you say give me the next one. So for instance, when I say for element in element, okay, we'll forget about this backslash here. Here the list is considered as a generator, which means that you say one, you say for each element, and you say to the list, do you have any more elements? Yes, give me, and you get the one, then the two, then the three. So what we're going to have is a frame generator, which is basically something that you can iterate over. So you can say for frame in my frame generator, and it's going to give you all the frames that you have in your audio. So basically, you don't have to cut it yourself. You don't have to make sure that you don't go over the end of the file, and then you have a frame which is not complete. Because if it goes over, then it completes it so that all the frames have the same size. So for instance, I'm going to go with a typical frame size 1000 and hop size. Some people are going to ask me, why this value? Why not like 1000 or why not 1 millisecond? It's like that because that's a power of 2, and the FFT which we're going to use after is very optimized if you have a size which is a multiple, which is a power of 2. So for instance, doing the okay, no, I'm not going to say how much faster because I don't know, but doing the FFT of 1024 sample is much faster than doing the FFT of 1000 samples, even though 1000 is smaller. So the idea is for each frame in my frame generator, and that's the way you would write it, which is very clean. So you would say, for instance, the spectrum here. So you have your frame, it's an audio frame, so it's 1000 samples. So what you want to do first is you want to window your frame. This. Once your frame is windowed, you want to compute the spectrum of it. And okay, so for instance, I will start with this, like spectrum equals spectrum. You see that once the algorithms have been instantiated, they work like functions. So for instance, here I can say spectrum. This is the one instantiated here. The windowing is here. So I can say spectrum of window of frame, and it's going to give me the amplitude spectrum.
Capital S or?
The classes have capitals. So for instance, what is it?
Does it affect the capitals?
Yes, it's it's case sensitive. And here, for instance, it's a class, so it starts with an uppercase S, capital S. All the classes, this is like common in lots of programming languages. The classes have an uppercase letter, and the variables, the objects or the instances, have lowercase. You could call it whatever you want. It's just a convention. It doesn't have to be, but it's like that so that it's easier to
Could you go back just for a second to where you assigned the audio file to the variable audio?
Yes, here.
Okay.
You will be able to share all this that you wrote maybe also later through the email or something.
Yes.
No?
Well, I can give you the whole history.
Yeah.
In the
I'm also
folder
copying.
actually that you can download from the website. There's well, feature extractor which contains a few of those things but in a single file, and there's going to be a few others we'll talk about quickly after. But if you want, I can give you the history of this.
Thank you.
Okay. Yes, so here I'm iterating over my frames. Sorry, you wanted to...
Oh, I got it.
Okay.
Thank you.
Well, maybe we can wait till we generate this, but I just have this, like a syntax question. So, for instance, for the windowing class, with the various parameters, if you did want to define size and type and zero padding, for example, how would you define that? Would that all be in one line, or would you define that?
Okay, yeah.
But we can do that after if you want.
Okay. Well, I just thought. So before I had it like that,
Right.
and you could separate it with commas. So for instance, type equals hand and zero having four colors.
But zero padding, you can write zero padding whatever you want. So
It's a parameter, and you can give it a value whatever you want as long as it's between 0 and
because it's a padding.
yeah, it's a parameter. If you write something which is not a parameter, for instance, like write zero pudding, this is not a parameter of window. Okay. This is wait. No. If you have those parameters, okay, that's another thing that's Python related, nothing to do with Essentia or anything. If you have those in a dictionary, for instance, because you read them from a config file or something, so let's say times equals dictionary, so that's types, which is and you have you cannot create it like that because terms is going to tell you some weird errors, but you're not supposed to you're supposed to give only named parameters. So like for instance, I say zero padding equals something.
Right.
Here it's not named, so even if I say params equals params, so that's a named parameter, but tell me okay, it's not a parameter. So how do you do it? So there's a way to do this for all Python functions. It's you put stars params. So we're stuck, but it turns your dictionary, like a single object which is a dictionary, into named arguments for the function that you are calling.
What is the meaning of dictionary in this?
The meaning of this?
The dictionary you are talking about.
The dictionary here is the type of parameters, but I showed you that if you want to actually compute, you have it. Oops. You have to do it like that. And you see that here, when you create windowing, you have, it's like a function, but you have two arguments. One which is type, okay, has the value hand, and the second argument is zero padding and has the value 124.
And in that case, 0 padding 1024 is related to 1024 FT?
Not directly.
I mean, how much 0 padding are we adding then to the...
Here you're adding 124, so basically it means that you have 124 of signal and 124 of zero padding, which makes the FFT size twice as big. So I put 124, so it's twice, so it's nice. You can put anything you want, but again, it's nice. Or for instance, if you are sure that you absolutely want frames of 1000, like that's great. But you want the FFT to go fast, you could zero pad it with 24 samples, and then you say, okay, so the FFT is on 124, but my input frames is like 1000 because I want it to be sliced always at 1000. But then this goes into like a signal processing consideration of like whether you have like time frequency resolution and everything.
Yeah.
It's just 124 because years of doing it like that. So
You can't, I'm sorry, one more question, you can't necessarily just define it as, you couldn't define zero padding as, like you couldn't define zero padding as a variable. You couldn't define the variable zero padding and then use that as a parameter inside of a class. Like if it were, say, it would be a multiple of something, like multiple of the window side, or multiple of the FFT side.
you can, but I mean,
Okay.
you can type it like that, but then you have to have frame size defined before.
Right.
It cannot be dynamic. I mean, at the moment where you give it here, it's computed here, and it needs to have a given value at that moment.
Okay.
What you can do is like at the top of your file, you write frame size equals whatever you want, top size, half of it, and then you use like those values or multiple of the values everywhere else in the time, but it has to be static. You don't have it like that. One thing though is for instance, the window and the FFT, as you saw, I didn't give them a size. Because you need to have it like the window needs to know that it's going to be 1000 something. This is because it resizes automatically. You don't have to. If you want, you can give it to it. So like the first time, it already knows it's going to be that size, and you don't need to resize it. That's just like a very small, tiny optimization because it's just not going to be computed the first time. But as much as possible, Essentia tries to be smart when it can be smart, and does not try too smart when it shouldn't be. Like for instance, resizing the FFT, okay, you say FFT size 124, and then you say, okay, here's the double, and the FFT says, like no, because it doesn't matter. Sometimes objects do not reconfigure themselves automatically. Actually, most of the time, they do not reconfigure themselves. For the FFT in the window, as you always do them, was kind of easier that way. Okay. Yeah, so here, okay, very quickly, I'm giving a function of, okay, maybe I'm digressing. This you do if you have a dictionary and you want to pass this dictionary as named parameters, also called keyword arguments in Python, because you have like type equals hand, zero padding equals this. If you have a list of parameters, so for instance, that's this, and you have a function that takes 3 arguments, you cannot call, if f takes 3 arguments, you cannot call this because it's only 1 argument with like 3 arguments. You would do it, but with only 1 star. Just, if you don't care, forget about it.
This is normal in Python, or
this is Python.
Yeah,
This is normal Python. Like 1 star is positional argument. Like you take a list, and each element of the list is an argument for the function. 2 stars is for keyword arguments. It's a dictionary, and all the elements in the dictionary is like are keyword arguments for the functions. Sometimes it's very helpful. Handy. But okay. So let's go back to my function generator. So okay, to do this, I get my spectrum, which is the spectrum of the window frame, and then I compute the MFCC. So as you remember, MFCC has, well, maybe you don't remember, the algorithm has 2 output values. One is the energy bands, and the other is the coefficients. So I could say coef. Let's say I don't care about the bands, so I could get them back in the value bands. You could use this, like underscore as a placeholder means it's a variable I don't care about, like don't even give it a name. So this is the MFCC of the spectrum, because the MFCC algorithm expects the spectrum. And now we would like to put those squares in a variable, which I will create, so let's just do nothing. So I'm going to create one now. So I could put them in a list, like MFC6 or MFCC list equals a list of something. And then I could do MFCC list dot append the MFC. I could add this line here in my loop, and that would be perfect. Now let's say you're not only computing the MFCC, but you're computing lots of descriptors. So you're not going to need a list, you're going to need a dictionary with all the names. And in fact, in Python that would be super easy. In C++, remember it was, it's not that easy because in C++ dictionary, it's called a map, you can only put objects which are the same type. So for instance, the coefficient, this is an array of values. It's like, by default, it gives you like 13 values. If I would put this in the C++ dictionary, I could only put values which have 13 coefficient. And then if you want to put something like the centroid, which is a single value, you cannot. So that's the reason that we have a class which is called the pool. So if you know Python, you know what a dictionary is. It's a Python dictionary, basically. And this is some object. And so, for instance, let's get the MFCC coefficients and the spectral centroid of all the frames in our pool. So I have my pool. I need the centroid algorithm, which I don't have, and I say that the range equals to so I do the same thing. I have my spectrum. There I have my conditions. And I have my centroid structure. So I want to add these in the pool, so I just pool, add, and I can give it a name. So I'm going to say, let's say it's low level descriptor, and I'm going to say centroid. This, yes, and I could call it only centroid. I'm calling it low level centroid for a reason, which we're going to see in a second. Yes. Okay. Now I have a pool which has 2 descriptors in there. In a pool, you can put stuff, and you have to give it a name, and the name you give it is separated by a dot. And this is because you can put stuff in a hierarchy, like the same as if it was a folders. like this is the same as if centroid was put in the low-level folder. So you can group stuff together. So for instance, if I would do this, I could put everything here in the low-level group, like namespace, and then I could compute some descriptors which talk about rhythm, and I put them in the rhythm. And you can have multiple levels, or you can have none at all, and it's all up to you. But it's a way to have it. And okay, and let's say you want to output this pool file on the disk. So there's one way at the moment. In Essentia, we use the YAML format. It's kind of like JSON, but more advanced. And so the algorithm that allows you to write stuff is called YAML output, and takes as input a pool. So it just takes the pool and puts everything into a file. And there's a few parameters, most important of which is the file name. That's it. So for instance, yes, here you can see the dot that I told you about that separates stuff. If you have a descriptor that's called this, it's going to be put in nested levels. So anyway, you just say, I want to write this to a file which is called mfcc.yaml. So this instantiates the object, doesn't do anything yet, right? Just creates the object that will do it, same as for the audio loader. And to call it, I'm calling it on the pool. Okay. Does this go too fast? Or still safe? Okay. Can I write it? That's the output object. Okay. Now it's an object that will output whichever, whatever I give it to, whatever I give to it, inside the file name that's put like that. So now I can output the pool, and now I should have an MFCC equals YAML file. If I look, yes, there it is. And if I look at that file, you can see it has some information which I can tell it to put there, that it always puts, like the version of Essentia. It has the low-level part, it has the centroid, so you can see all the values for the centroid. So there are quite a bit of them. And then the values of the MFCC coefficient. So it's not very clear because there is a lot of them. But this is a list of arrays. So that's the first value. You have, that's the energy. That's the second value. But okay, there you have it. Usually, that's too much information that we can deal with because it's huge. And this was, this was for a file that's not even 10 seconds long. If you take a song that's 5 minutes, it's gonna be way, because as you can see, this is like half a megabyte already. So what we want to do is, instead of saying we're going to output the MFCCs for all the frames, we're saying it would be much more useful if we could have a compact representation for this information that we could use when comparing some songs. For instance, maybe all the MFCCs for all the frames is too much, but if we had the mean of those coefficients, maybe we could do some comparison. Or if we had the variance, for instance, we could decide whether there's lots of stuff that changes in the song or not. And basically, you want to do some sort of aggregation because the volume of data that you're dealing with is way too much. So to do this, there's this algorithm which is called full aggregator. Takes a pool and outputs a pool also. So we're talking about the same kind of data here. And you can tell it what it should compute. So by default, it does mean, variance, minimum, and maximum. But you can choose any one of those. So these basically are all the algorithms that you can find in the statistic part. Well, that's it. I'm not going to go over all of them. Let's just say that we want to compute the mean and variance of our MFCCs and of our centroid, and we're going to be done. So to create it, I say class equals I want the mean and I want the variance.
And if we want to take a look to the YAML in the Windows, they'll have to be editors.
No,
I mean, the cat, look at the cat is not working.
yes. I don't know. On Windows, I guess you will have to open the folder with the Explorer and pick up the file. Unless you have something that you can call from the command line in Windows directly. But type on Windows. Yes. This is like the
See what cat.
cat. I don't know why Windows. Type.
Not in the Python command as ls or cd.
Yes, yes. You need to put the
Okay.
exclamation mark in front of it.
Is there a way to print the pool on the terminal?
Yes. If you look at the YAML documentation, it says that the file name by default is a dash, which means that if you use dash, it prints it to the terminal. So if I have my I just say YAML output, I create it with no arguments, so it takes by default, and I print my pool, it's going to print it directly to me. Okay, so I want to, that's too much information, so I want to create something that aggregates my information. So I aggregate the pool, and let's say I'm going to print it directly. So I just YAML output of this. So here I'm chaining multiple things at the same time. So I create a YAML output instance, right? Default parameters. So by default, instead of writing it into a file, it's going to print it to the terminal. And then I call it here on the aggregated pool, okay, which will compute the mean and the variance of the pool. This gives me back a pool, and this pool I print it on the terminal, and obviously anything. I'm going to print it to a file because this file it only works once here. Name was MFCC.
Is there any way to stop? We have to start.
Yes, I'm just finishing this, now it's the break, and the second part is going to be easier.
But we know to break the command, I mean, I have like a 1 minute 20 second zone and it's plotting MFCC, like.
You can type Ctrl C and then cross your fingers. Otherwise, you can Ctrl Z and then kill it, but then you kill everything.
Control C is not working.
You have to wait then.
Close the window.
Yes.
But no way to stop it like in Matlab.
It's Control C normally, but when it's inside, Control C can only break it in between Python function calls, and when it's inside a single call, you have to wait for that single call to finish. So you're okay, so I just wrote it. So I didn't show you, but in the pool originally, there's a break coming in 5 minutes, don't worry. We had the low-level centroid and low-level MFCC, and then I said, okay, aggregate with min and var, and now you see that we have low-level centroid.min, low-level centroid.var, and the same goes for the MFCC. And if you look at the file that I just wrote, it's all in there, and it's much easier to read because that's the full file. Before it was like, you see, stopping the screen, and you cannot do anything anymore. Here you have low-level centroid. Before you had here, you had all the values for the centroid, like now it's a group, and inside that group you have mean and variance of that centroid. And this is quantity of information that we can work with, and next week we're going to see that with this information we can do lots of stuff with audio linearity and whatnot. End of the first part. Can I have a break?
Yes, please.
It's possible to export the word, I don't know how that's called, the workspace.
Yes.
It's possible for you to export it to me? Because I lost the part of the colon.
Yes. Well, I'll send it, but basically just history, and it gives you everything that you've done.
Just export the history comment.
Yeah. Okay. Yeah, I'll send it by mail.
Okay.
Mailing, which is a common Google